Hello, I am Karthikeyan, Hydrogen R&D Engineer at the Florida Solar Energy Center, University of Central Florida. In this research, supported by NASA Glenn Research Center, we are developing a process to produce hydrogen based on supercritical steam reformation of used lubricating oil. Used lube oil can be valuable as a re-refined lubricant or as an energy source.
The significance of this research is that it has potential to produce hydrogen for NASA at a much lower cost. Lube oil is a complex mixture of low and high molecular weight hydrocarbons. Typically 75 weight percentage aliphatic hydrocarbons, 15 weight percentage polyaromatic hydrocarbons, and various other organic and inorganic additives. Since lube oil is a complex mixture of various hydrocarbons, it is very difficult to break down its constituents using thermal energy alone. At the Florida Solar Energy Center, we are developing a thermocatalytic process that uses supercritical steam to reform lube oils into clean hydrogen. Water becomes a supercritical fluid at temperatures above 374 degrees Celsius and pressure over 22.1 megapascal. In the supercritical region, densities are a fraction of that of normal liquid water, while solubility is closer to that of high-pressure steam. A key advantage of chemistry in supercritical water is that it becomes possible to vary the properties of the reaction medium by manipulating the pressure and temperature and optimizing the reaction without changing solvent water. Many small polar and nonpolar organic compounds are completely miscible with supercritical water. Also, many large organic compounds and polymers hydrolyze to smaller molecules at typical supercritical water conditions, and thus solubilize via chemical reaction. The ease of dispersion of the organic and oxidizing species within a single supercritical phase, in conjunction with high diffusivity, low viscosity, and relatively high density of supercritical water reaction medium, results in very rapid reaction kinetics. We are conducting bench-scale experiments to reform lube oils to hydrogen gas. The test rig is made up of 4 zones. They are the feed preheat zone, the reaction zone, the product separation zone, and the product analysis zone. In the feed preheat zone, oil and the water are pumped at 22.1 megapascal pressure using HPLC pumps. The water and oil are heated to a temperature of about 350 degrees Celsius before entering the reaction zone. Reactions occur within an inconal reactor, within which the reactants are heated up to 375 degrees Celsius in the presence of a catalyst. Fluid pressure and temperatures are monitored, continuously, at the inlet as well as at the outlet of the reactor. In the separation zone, the product liquid gas mixture passes through a back pressure regulator that reduces the high pressure to near atmospheric. Then the low pressure, high temperature liquid gas mixture enters a condenser where the liquid and gaseous components are separated. The gaseous portion is directed for analysis. The liquid portion is collected at the condenser bottom for later analysis. In the product analysis zone, most of the output gas passes through a bubble flow meter and then is vented out. However, a small portion of the output gas is sampled into a gas chromatograph, where it is analyzed for hydrogen, carbon dioxide, carbon monoxide, and hydrocarbons. For safety, the reactor is shielded while in operation, and all process parameters, including the flow rates, temperatures, and pressures, are controlled at a distance from the reactor. In addition, a pressure relief valve has been installed, and special corrosion-resistant steel tubing and fittings are used throughout. NASA now pays more than $4.50 per kilogram of liquid hydrogen. Our process, if successfully developed, can produce hydrogen at the much lower cost of about 40 cents per kilogram of hydrogen. Floridians generate close to 45 million gallons of used lube oil each year. This is enough to support more than 100 shuttle launches per year.
The current research effort is directed toward identifying active catalysts that improve the yield of hydrogen production from used lube oil. To date, We have operated this system successfully and demonstrated continuous hydrogen production. This process is selective toward hydrogen production with minimal byproduct formation. Special thanks to NASA in support of this research project.